The purpose of a communication system is to transmit information bearing signal from the transmitting end to the receiving end through a communication channel. The three basic building blocks in any communication system are the transmitter, the channel, and the receiver. The transmitter puts information from the source onto the channel. The channel is a medium for transmitting information to the receiver. The channel can be free space, it can be wired or unwired. The original message usually contains frequencies in the low frequency range or audio frequency range. Therefore, some form of a frequency band shifting or conversion to a high frequency range is necessary in order to make the signals suitable for transmission. This shifting in the range of frequencies is achieved by a process known as modulation. A communication system transmits information from the transmitting end to the receiving end. So the transmitting end will capture input signals from devices such as microphones or CD player. The magnitude of such a signal will be very low. So the transmitter will have to amplify the signal, and it will have to encode it into a form suitable for transmission through the channel. Then it will have to modulate the signal to high frequency range so that this information can be transmitted over long distances, and then it will have to be power amplified and transmitted through the channel. So when the signal is being transmitted through the channel, it will encounter noise. So noise is any unwanted form of energy that will interfere with the communication system. So noise will be added to the message signal through the channel. At the receiving end, the received signal will be of very low magnitude, because when the signal is transmitted to the channel, it gets attenuated by the various factors within the channel. So the receiver will have to amplify the signal, decode it, demodulate it, and reproduce it with the help of any reproducing devices such as a loudspeaker. We will now see the various frequency band allocations. Frequencies from 10 to 30 kHz are classified as very low frequencies, or VLF. They are used for applications such as telegraphy. 30 to 300 kHz frequency range is classified as low frequency range, and they are used for marine navigation. 300 to 3000 kHz are classified as medium frequency range, and they are used for broadcasting. AM broadcasting frequencies fall within the medium wave frequency range. Frequencies from 3 to 30 MHz have been included in the high frequency range, and they are used for long distance communications. Very high frequency range includes frequencies ranging from 30 to 300 MHz, and they are used for TV and radar applications. Ultra high frequency range falls within the 300 to 3000 MHz, and they are used for short distance communications. Frequencies from 3 to 30 GHz are classified as super high frequencies, and they are used for satellite communications. Frequencies from 30 to 300 GHz are again classified as extra high frequencies, and they are reserved by the government. AM broadcast range for medium wave broadcast falls within the frequency range 535 to 1605 kHz, and they are classified into medium frequencies. Shortwave broadcast range is from 3 MHz to 30 MHz, and it falls within the high frequency range. FM broadcast range is from 88 to 108 MHz, and it falls within the very high frequency range. Whereas the broadcast range for television programs is from 47 MHz to 870 MHz. Now we will see what modulation is. Modulation may be defined as a process of combining a low frequency signal with a very high frequency carrier wave. Some of the characteristics of the carrier signal will be varied in accordance with the amplitude of the message signal. If the carrier is a sinusoidal wave, then the process is called continuous wave modulation. The message signal or the baseband signal is called the modulating signal. The resultant wave of the modulation process is known as a modulated wave. Modulation is performed at the transmitting end of the communication system, and at the receiving end, the original message is restored by a process known as demodulation, which is the reverse of modulation. And modulation essentially is varying one or more parameters of the carrier wave in accordance with the instantaneous magnitude of the modulating signal. The modulating signal contains message, the carrier frequency contains no message and is a high frequency wave. Now we will see why modulation is needed. The first point is that the modulation helps reduce the size of the antenna, because as the result of modulation, a low frequency message signal is converted into a high frequency modulated wave. The length of the antenna can be reduced. As you can see that the length of the antenna is inversely proportional to the frequency by the relation L is equal to C by 4f. This means that as the frequency is increased, the length of the antenna can be reduced. Again, modulation allows several broadcasting stations to transmit simultaneously at different carrier frequencies, and it permits multiplexing, that is, several signals can be transmitted through the same channel without mixing. So the modulated signal is of high frequencies and noise is added to the message while it is transmitted through the channel. So high frequency signals are less prone to noise. This means that modulation is necessary to reduce noise and interference and transmit the signal over long distances. It thus helps to improve the signal to noise ratio. In analog modulation, the modulating signal will be a continuous time varying signal. So analog modulation can be classified into amplitude modulation as well as angle modulation. Angle modulation can again be classified into frequency modulation and phase modulation. In amplitude modulation, the amplitude of the carrier is varied in accordance with the instantaneous amplitude of the modulating signal, whereas in frequency modulation, the frequency of the carrier is made to vary in accordance with the instantaneous amplitude of the modulating signal. In phase modulation, the phase of the carrier is made to vary in accordance with the instantaneous amplitude of the modulating signal. So frequency modulation and phase modulation are together classified as angle modulation. In amplitude modulation, the magnitude of the carrier wave is made to vary in accordance with the instantaneous amplitude of the modulating signal. You can see that the modulating signal is of the form Em is equal to Em sin omega mt, where Em is the amplitude of the modulating signal, omega m its angular frequency. The carrier wave is Ec is equal to Ec sin omega ct, where Ec is the carrier amplitude, omega c again its angular frequency. So here the amplitude of the carrier wave is varied in accordance with the instantaneous amplitude of the modulating signal. So you can see that in the modulating signal, the carrier amplitude is made to vary in accordance with the instantaneous amplitude of the modulating signal. The resultant modulated wave will be of the form Ec plus small em sin omega ct. So the amplitude of the carrier wave is varied according to the modulating signal. They are reserved by as an illustration of amplitude modulation. This is the modulating signal. Em is equal to Em sin omega mt. It is of low frequency and contains information. The carrier signal is a high frequency wave. Ec is equal to Ec sin omega ct and does not contain information. The modulated signal will have its amplitude varied You can see that the frequency spectrum of amplitude modulated wave will comprise of the carrier, the lower sideband, which is the difference frequency omega c minus omega m, and the upper sideband, which is some frequency omega c plus omega m. Both lower sideband and the upper sideband contains information and the same information, so we actually need only one sideband. The carrier does not contain any information and can be eliminated. In frequency modulation, the frequency of the carrier is varied in accordance with the instantaneous amplitude of the modulating signal. You can see that in the modulated wave, the frequency part of the carrier is varied. E is equal to sine omega ct plus mf cos omega mt, where mf is known as a modulation index. This is an illustration of frequency modulation. You can see that the message signal or the modulating signal is EM. The carrier wave is EC. It has fixed amplitude and frequency, and as a result of modulation, the carrier frequency is made to vary in accordance with the instantaneous amplitude of the modulating signal. You can see that as the message signal increases in amplitude, the frequency increases and it will be at its highest at the peak of the modulating signal. Then the frequency decreases as the carrier amplitude decreases, and as the carrier amplitude reaches a minimum, the frequency will be minimum. Again, the carrier the amplitude of the message signal increases, the frequency of the modulated signal increases, and it will be at its maximum at the peak of the message signal, and then it decreases. So you can see that an FM wave, the frequency of the wave, carrier wave, will be varied in accordance with the instantaneous amplitude of the modulated signal. The frequency will be at its highest when the message signal has maximum amplitude. The frequency will be at its lowest when the message signal has the least magnitude. We can also see that the frequency of the modulated signal is varied, but the amplitude of the modulated signal will remain constant. Now we will bring out a comparison between AM and FM. In FM, all the transmitted power is useful, whereas in AM, most of it is in the carrier. The carrier does not contain any information in AM. Again, FM is highly immune to noise on account of the following reasons. So, there are amplitude limiters used in FM receivers which remove any amplitude variation occurred due to noise. Most of the noise occurs as amplitude variations and will be removed by an amplitude limiter at an FM receiver. FM is used in the VHF UHF range, which is less prone to noise, whereas AM uses a medium wave and high frequency range in which noise is more. Again, in FM, only a fraction of a watt of audio power is required to produce 100% modulation, whereas a larger power is required in AM. The amplitude of FM wave remains constant, which is independent of modulation index, whereas in AM it is dependent on modulation index. We will also see what are the drawbacks of FM when compared to AM. FM produces infinite number of sidebands, which means that a large bandwidth is required to transmit FM. FM systems are complex than AM. The transmitters and receivers are more complex and have more circuitry than AM transmitters and receivers. Again, FM is used for line of sight communication and range is smaller than AM. Thank you for your patient listening.